Welcome back, everybody. In our last section in the identities chapter, we're talking about a new set of identities, the sum and difference identities. Okay, so we'll give you a new set of identities today, and we'll show you some different stuff we can do with them here. All right, so here's our first set of sum and difference identities for the cosines and the sine functions. Okay, two for each, and when I say sum and difference, what we're talking about is either the sum of two angles within a trig function, or the difference of two angles within a trig function. Okay, so notice we have a sum and a difference for both the sine and the cosine functions. Okay, now we'll use these identities in both directions. We'll work from left to right and right to left. Now, a few things to notice about them. First off, with the cosine, it goes cosine, cosine, sine, sine for both the difference and the sum. Whereas with the sine, it goes sine, cosine, cosine, sine for both of them. And then also notice with the cosine, the signs don't match. When we're subtracting within the cosine, it's going to be adding outside of it, whereas with we're adding and subtracting. And then with the sine functions, the sine signs match up. The plus goes with the plus, minus with the minus. Okay, so a little bit of look tricky right off the bat, but once you use them a little bit, you'll recognize they're not too bad. Let's take a look at how to use these. I'm not going to prove them for you here. That'll take 10 minutes. We're not going to waste your time. Let's just get into using these identities. Now, one thing we can use these identities for is to evaluate trig ratios for angles that we weren't able to do in the past. We'll show you what we mean by that. Problem 1 says, find the exact value of cosine of 5 pi over 12. Okay, now 5 pi over 12, that isn't one we've seen very often before, so let's convert that to degrees right off the bat. Remember, we can do that by taking the 5 pi over 12 and multiplying by 180 degrees over pi. And when I do that, I end up with a 75 degrees. Okay, so cosine of 5 pi over 12 is the same thing as cosine of 75 degrees. Now, in the past, when we've evaluated trig ratios by hand, we've only been able to do multiples of 30, 60, and 45, and 90, I suppose. Okay, because those are ones we had special right triangles for or could use quadrantal angles. Okay, what we're going to see here is that our sum and difference identities allow us to evaluate some different angles here. Okay, now the trick is going to be writing this 75 degrees in terms of angles I know how to find the sines and cosines for. Remember, the angles we know are 45, 30, and 60. Okay, coming from our 45, 45, 90 right triangle. Okay, which had sides of 1, 1, and root 2. That was one of our special right triangles. Okay, and then also we said we had the 30, 60, 90. With side lengths of 1 across from the 30, root 3 across from the 60, and then 2 is the hypotenuse. So if you told me to find a trig ratio for any of these angles, 45, 30, and 60, we could do that because we have our special right triangles. So the goal here is going to be to write 75 in terms of these angles I know how to deal with. Okay, well, 75 is 45 plus 30. So I'm just going to rewrite this as the cosine of 45 degrees plus 30 degrees. And then what that's going to allow me to do is apply my sum and difference identities, which I'm going to pull up here, okay, to actually evaluate this. Okay, now I've compacted those four identities into two of them here, and I'm using the cosine one because we have cosine of plus plus. So I'm going to rewrite this as, using this top identity, the cosine of the first angle. So say cosine 45, all right, times the cosine of V, the second angle. And then notice the way I have this written, I have it as cosine with a plus minus and a minus plus here. That just means whatever the sign is in the first case, you're going to flip it for the second case. So since I have addition, I'm going to flip that around to subtraction and go sine of my first angle. So sine 45 times sine of the second angle, sine 30. We'll get these out of the way as we work through the rest of the problem. And then from here, once we have this split up into smaller chunks that we're all able to evaluate, what we can do is just evaluate each chunk individually and then add it all together at the end. Okay, so let's go through that. Now we're back to our first trig chapter, basically lesson 1 of trig. Okay, cosine of 45, we take a 45-degree angle. Cosine is adjacent over hypotenuse, so we'll say that's equal to a 1 over root 2. Okay, times the cosine of 30. Again, cosine is adjacent over hypotenuse, so we'll go root 3 over 2. Then we'll go subtract. We need to figure out the sine of 45. Okay, sine is opposite over hypotenuse, so we'll go 1 over root 2. Times the sine of 30, that would be an opposite 1 over hypotenuse 2 for this 30-degree angle here. Okay, so times 1/2. Okay, let's start putting this mess together here. Now notice I have some fractions, but they have a common denominator. This set's going to have a 2 root 2, as with our second set. So I could rewrite this as 1 square root 3, which is just square root 3, minus a 1 times 1 is 1. All right, all over a 2 root 2. Okay, and I'm going to be able to take one more step with this to clean it up. If I multiply the top and bottom by a root 2 over root 2, that's going to allow me to rationalize by the denominator. Okay, that'll cancel out this root 2 on the bottom. I'm going to need to distribute that to both terms on the top, which will leave me with a root 6 minus root 2. All right, and over on the bottom then, this root 2 times root 2 is just a 2. So in other words, we have a 2 times 2, which would be a 4. All right, that's my final answer. That's as simple as I can make this. Can't combine these roots because they're not the same. All right, there you go. Okay, again, the process there was take the angle that we can't evaluate by hand, split into angles that we can evaluate by hand using special right triangles, apply our sum and difference formula, and then just evaluate all the pieces and add it together. Okay, problem B is the same deal. Okay, works out pretty much the same way. Why don't you pause the video, work through that problem, or get as far as you can through it, and then hit play. We'll run through the answer, and you can check your answer that way. All right, after you've given part B a shot, let's take a minute and run through this. Okay, first off, let's figure out what this negative pi over 12 is equal to. Okay, if you convert that, that's negative 15 degrees. So we could say we have the sine of negative 15 degrees. And writing that in terms of 45s, 30s, and 60s, there's a few ways to do that. Basically, I'm going to say this is the sine of, we could say 30 minus 45. That'll give us a negative 15. Okay, and I'm going to pull up my identities here just so they're handy and I can use them. Okay, we've got the sine of a difference, so that's going to be the sine of the first angle, sine 30, times the cosine of the v, the second angle, times cosine 45. And with the sine ratio, it's plus minus, so that sine's going to stay the same. We'll say minus cosine of the first angle, cosine 30, times sine of the second angle, sine 45. Okay, so we split this apart into smaller angles that we can deal with, that we know how to deal with. Just a reminder what those 45, 45, 90, and 30, 60, 90 right triangles look like. It's a sloppy triangle here, but it'll work. 1, 1, root 2, and then okay, doing this a piece at a time. Sine of 30 is going to be equal to 1 over 2. Okay, cosine 45 is going to be if we use this 45 here, 1 over root 2 again. And then minus cosine 30 would be a root 3 over 2. And sine 45 will be a 1 over root 2. Okay, notice this ends up pretty much the same setup here. Okay, the slight difference between the two kind of ways these work out. That's the nice thing about them. You're always going to get a similar looking answer for these kind of problems. So I combine these fractions. We have a 1 minus root 3 all over 2 root 2. And then my last step, we'll rationalize, we'll multiply by root 2 over root 2. And that's going to give me a root 2 minus root 6 all over 4 once again. Okay, again, similar answer. You're always going to have a 4 on top. You're going to have a root 2 or root 6 for a problem like this. The difference is going to be is which one's positive, which one's negative. Our last answer, we had a root 6 minus root 2. Okay, this one's just slightly different. But if you're getting something that looks like this, you know you probably did the question right. All right, in problem 2, we're going to show you another way we can use these trig identities. Okay, in the first problem, we worked from the left side of the identities to the right side. Here we're going to be doing the opposite. So problem 2 says, find the exact value of the expression of cosine 155 times cosine 35 plus sine 155 times sine 35. Now, 155, 35, those are not multiples of 30, 60, 45, or 90. So I'm not able to figure out what the sine or cosine of those angles are directly by hand. Okay, but what I can do with this problem is I can use my sum of difference identities backwards to rearrange it into something that hopefully I can evaluate by hand. Okay, now my setup here is cosine, cosine, sine, sine. So now I'm talking about the cosine identity. And since there's a plus in between, I'm going to flip that sign to a minus within the cosine ratio. Okay, so we'll rewrite this as the cosine of 155 minus 35, okay, which is equal to the cosine of 120 degrees. All right, that is a multiple of 30, 60, or 45. Okay, so the work with the identities done, this is something I can actually evaluate by hand and something we've been doing since our first trig chapter. Okay, reminder how to do that. Let's graph 120 degrees in standard position. Okay, we'll put the start of our angle on the positive x-axis. We'll open up past 90 but short of 180 to the second quadrant. We'll say this is what 120 degrees looks like. We'll make a reference triangle where my reference angle here is 180 minus 120, which would give me 60. Okay, so it looks like we're talking about our 30, 60, 90 right triangle with sides of root 3 across from the 60, a 1 across from the 30, and that'll be negative because we're in the negative x direction, and a 2 for hypotenuse. All right, based on that triangle, I can evaluate this cosine of 120. Cosine is just adjacent over hypotenuse. Adjacent is negative 1, hypotenuse is 2. So my answer here then is a negative 1 over 2. All right, again, a little review from something we did months ago. Okay, but the idea here is to take this complicated expression, use our sum and difference identities to write it down into something simpler, something we know how to evaluate, and then just evaluate that. Okay, that's part A. Once again, pause the video, work through part B, and then hit play to get an explanation or to check your answer. Part B, same idea. We want to use our identities to write this as a single trig ratio. Okay, now this time we're looking at sine, cosine, cosine, sine. So I know that's going to be my sine sum of difference pattern. So I can rewrite this as the sine of 137. And in this case, we're going to have since there's a plus in between, the sine will stay the same. There'll be plus inside the angle. So plus 88, which will give us the sine of 225. Again, this takes us back to our first trig chapter, so we're done with the identities here. We'll graph that angle in standard position. 225 is going to be in the third quadrant, short of 270. Make our reference triangle. If I go 180 minus 225, or 225 minus 180, we get a 45 degrees. Okay, meaning this is the 45, 45, 90 with side lengths of 1, 1, and root 2. Okay, both the opposite's negative and adjacent's negative in this case. And we can say our sine ratio is equal to the opposite of 45, negative 1, over the hypotenuse, square root 2. Okay, which, if we rationalize, we end up with a negative root 2 over 2. Today we're also going to look at the sum and difference identities for the tangent function. Okay, and there's two of those, one for the sum, one for the difference. And notice these two identities are the same thing except for where the positive and negative symbols fall. With a sum identity, we have a plus on the top, minus on the bottom. And then with the difference identity, it's minus on top, plus on bottom. So really the only difference is where these positive and negative symbols fall. And just like we did with our sine and cosine identities, I can combine both the sum and difference into a single equation. We could say tangent of u plus or minus v equals tangent u plus or minus v, plus or minus because this sign will stay the same, over 1 minus plus, so my sign is going to flip, tangent u times tangent v. Okay, so let's go through this. Similar problem to what we just did with sines and cosines. We want to figure out what the tangent of negative pi over 12 is. Now, that's the same thing as the tangent of negative 15 degrees. Okay, so we can convert that angle to degrees. We've already dealt with this one. And just like we did with sines and cosines, I want to write negative 15 in terms of 30s, 45s, or 60s. So I'm able to evaluate these a piece at a time. So I'm going to rewrite this as the tangent of, we'll say, 30 minus 45. All right, and then from there I can apply my identity. We can rewrite this then as the tangent of the first angle, 30, all right, minus the tangent of the second angle, the 45, okay, all over 1 plus, because we're going to flip the sign here, tangent the first angle, tangent 30, times tangent of the second angle, tan 45. I'm leaving myself a lot of room here just because this problem is going to take up a lot of space. Okay, so once again using our special right triangles, we have the 45, 45, 90. And the 30, 60, 90. We can evaluate each of these chunks individually here. Okay, tangent 30, if I take my 30 degrees, that's going to be opposite over adjacent, so that'll be a 1 over root 3. And it's actually this 30 degrees that's going to make this problem ugly, so avoid that if you can, but we'll show you how to deal with it in this problem. All right, minus tangent 45, if I take a 45, opposite over adjacent, that's just going to be a 1. We'll call this just 1 over 1 to keep it a fraction. And then all over 1 plus tangent 30 again, which is the same 1 over root 3. Okay, times tan 45, which we can say is a 1 over 1 once again. Okay, now the real work for this problem is going to be reducing this down. That's going to be the messy part. So we're done with our special right triangles. I'm going to get those out of the way just so I have room to work. And I'm done using the identities. I'm just going to get that out of the way as well. And let's start up top here where we have some room, or keep working up top here. All right, so first thing I want to do is I want to combine these fractions in my numerator and denominator. Okay, to do that I'll need a common denominator. So I'm going to multiply this fraction by a root 3 over root 3. Same thing for this fraction, this 1 over 1 we can multiply by root 3 over root 3. That's going to allow me to add these together. So in the numerator I can say I have a 1 minus root 3, all right, over root 3. Divided by denominator we'd have a root 3 plus 1 over root 3. Okay, so still looking ugly, but we've turned this into a single fraction in the numerator, single fraction in the denominator, rather than two. Alright, so I can take care of my division of fractions by switching to multiplication. We can say this is the first fraction flipped right side up, so 1 minus root 3 over 3. Okay, times, over root 3, times the second fraction flipped upside down, so that'd be a root 3 over root 3 plus 1. Now, a nice thing happens here is one of our root 3's cancel, so things are starting to look simpler. So we have a 1 minus root 3 over root 3 plus 1. Okay, still looking ugly here. Now this is where I'm going to have to rationalize my denominator. I want to get the root 3 out of the denominator. And to do that, what I need to do is multiply the top and bottom of this equation by the conjugate of my denominator. So that'd be a root 3 minus 1 over root 3 minus 1. And what that's going to do is it's going to clean up the denominator. It's going to leave me with a nice number. Roots will be gone. And we'll show you how that works again here. So in the numerator, I do need to FOIL these two together. Okay, so first, 1 times root 3 would give me a root 3. Outer, 1 times negative 1 would give me negative 1. Inner, negative root 3 times root 3 will be just a negative 3. And then last, negative root 3 times negative 1 will be a positive root 3. Okay, denominator will FOIL as well. First, root 3 times root 3 is going to be a 3. Outer, root 3 times negative 1 will be a negative root 3. Inner, 1 times root 3 would be a positive root 3. And that's the whole reason we did the conjugate, because that inner and outer will always cancel out. So you can actually skip that step. And then last, 1 times negative 1 would be just a negative 1. Okay, last step here, we can clean this up, and I'm just going to go up here where I've got some more space. Okay, I have a root 3 plus a root 3. We could say that's just 2 root 3. And then a negative 1 minus 3 would be negative 4. All right, all over 3 minus 1, which would be a 2. And then the last step, finally, I can reduce this. I can reduce the 2 and the negative 4 with this 2, and say we end up with a root 3 minus 2, because I have to divide both these terms by the 2. Okay, that's my final answer. A lot of stuff happening here. Okay, but the nice thing, just like with sines and cosines, with the tangent, you're always going to end up with an answer that looks like this. Okay, so when you get done, you know you did it correctly. And then also, like I said, this is the ugly example. Because I used this tangent 30 and got the 1 over root 3, okay, if I can avoid that 30, I can actually avoid all this work until I get to this point here. Then I still need to rationalize, but it's a lot less work for that problem. That's the way part B is going to work out. Why don't you pause the video, give part V a shot, and then hit play so you can check your answer. We'll run through that one together. All right, so going through B, okay, tangent of 7 pi over 5 is the same thing as the tangent of 105 degrees if I convert. Okay, which, if we rewrite in terms of 30s, 45s, and 60s, we could say is the tangent of 45 plus tangent of 60. And if I convert that using my sum and difference identity here, that's going to be the tangent of 45 plus tangent 60. All right, over 1 minus tangent 45 times the tangent of 60. Okay, identity's done. We'll get that out of the way. Okay, we can evaluate each of these parts here. So I'm just going to go over here. This one won't take up quite as much room as the last problem. Tangent 45 is just a 1 once again. Tangent 60 is a root 3 if I use my special right triangles. Okay, root 3 over 1, which we'll just call a root 3. Okay, so no extra fractions in the numerator. And then we have 1 minus tan 45 is 1, and then tan 60 is root 3. Okay, so there's 1 minus root 3 in the denominator. Okay, so right off the bat, this one looks a lot nicer just because I don't have a tangent 45 anywhere in sight here. Do still need to rationalize this. We'll multiply by conjugate to the denominator. There'll be a 1 plus root 3 over 1 plus root 3. Okay, in the numerator, we have to FOIL. First will give us a 1. Outer will give us a root 3. Inner will give us another root 3. And last, root 3 times root 3 will be a plus 3. All right, all over in the denominator, we can do the first and last, skipping the outer and inner. Okay, we have a 1 times 1 is a 1. Okay, the root 3 and negative root 3 would cancel once again. Okay, then for the last, we have a negative root 3 times a positive root 3. That'll just be a negative 3. Okay, cleaning this up then, 1 plus 3 is a 4. Root 3 plus root 3 is just a 2 root 3. So this is looking similar to our last question. And then 1 minus 3 would be a negative 2. All right, so we can finish this off as 4 divided by negative 2 would be a negative 2. And 2 divided by negative 2 would be a just negative 1. So we could say minus root 3. All right, so there's our answer. Again, similar to the last problem, just differences really are negative, positive symbols. All right, so there you have it, our sum and difference identities. Kind of ugly formulas, but like you saw, they kind of always work out the same way every time. Okay, so a few repetitions through these, you'll have them. And really, there's not a lot of variation we can put in these problems. Okay, by the time you get to the test, you'll have seen these questions through the homework. All right, so give the homework a shot, get help if you need it, and we'll see you later.